Okay, welcome to my YouTube channel, Physics Matters. Today we will talk about another important subject, and this is called equation of motion. Yeah, this is one of the most important subjects in kinematics because this equation, or actually it's a set of equations, so to say. Yeah, this set of equations will help us to determine the speed and also the velocity in general, and also the position of any object in three-dimensional space at a given time t. Yeah, and before we can derive this, I would like to shortly revise what we have discussed before. So we have already discussed about speed and distance, or speed and position, both. And we were able to derive one from the other. So for example, we said in that the speed v is given as the derivative of the position with respect to the time, ds over dt. And we said already that the acceleration of an object is given as a equal to dv over dt. And now what we want to do, we actually want to find a way how to convert acceleration to speed. And in order to do this, we take again our equation here, a is equal to dv over dt. And what we will do now, we will multiply both sides with dt. Yeah, I know it's mathematically not perfectly correct, but from the physics point of view, it works very well. So just to show how it works, we can do it in the following way. This leads to a dt, and here on this side only dv remains. And now what we can do in the next step, we can calculate the integral because we have differentials here, and at the end this leads to integral a dt, which is equal then to the integral over dv. And here we have time, so we go from t1 to t2, and here we have speed, so we go from v1 to v2. And this here we can solve easily. This is nothing else than the distance, then the difference in the speeds, which is delta v. Yeah, so what we can learn from this is that any change of speed, delta v, is given as the integral from t1 to t2 over a dt, and that the distance can be calculated, delta s can be calculated as the integral from t1 to t2 over v dt. So what these equations actually say is that distance is equal to the area in a VT diagram and that speed is equal to the area in a AT diagram. Yeah, we have already seen ST diagrams and VT diagrams. And now we can also define AT diagrams in the same way. We have the acceleration on the y-axis and the time on the x-axis, but nothing else changes. Let's take a look at the VT diagram, which is easy to understand. So we have here our v on the y-axis, t on the x-axis, and we learned already that if we have a constant speed, then this is equal to a horizontal line in a VT diagram. So now we can define here an interval of 2 times, for example here and here. This would be our t1, this would be our t2. And of course then this part here between these 2 times is our delta t. And in the same way, we can also then say that this interval on the y-axis is simply v, because v is constant. So then, if we want to calculate our delta s here, this would be simply given as v times delta t. Yeah, this is also a formula which we have derived earlier. So here in this case, it makes perfectly sense. And now we can draw another VT diagram, yeah, with a little bit more complicated function. So this could, for example, look like this. And then we can calculate, or we can define again another interval, for example this one. Again we have t1 and t2, but now we cannot say anymore that delta s is equal to v times delta t, because v is not constant, it changes in time. So the only possibility to really calculate this integral under this graph here, or this area, is by writing delta s, which is equal to t1 to t2 of v dt, where v by itself is a function of time. So again, let's make an example to understand it better. So we can, for example, draw a car here. Again, we use a car, but it could be also any other object. And this car has an acceleration a, which is, for example, 5 meters per square second. It's a little bit, maybe a little bit too much for a car. It's half of the g factor, but let's just take it as an example. And now we have an initial speed of this car at the time when we measure, at t equal to 0, which is given as 3 meters per second, and we have an initial position of that car, which would be called S0 equal to 10 meter. So what it means actually that we have here acceleration a, and we have an initial speed v0, and we have a distance already from the beginning, which could be, for example, here, and this is given as S0. Yeah, and what we want to do now, we want to actually calculate the speed v and the position s at a given timestamp, for example, 2 seconds. So the first thing which we will do, we calculate the speed. So we know that, or we learned already before, that v of t is given as the integral of a dt. And a is constant, it does not change in time, so this can be solved easily. This is simply a times t plus the integration constant c1. Now the only question is, what is c1? We don't know at the moment what it is, but I already choose the right color for that. So we can do the following. We can now calculate it by using our boundary conditions. So we say v of 0 seconds at the beginning, we know already, this is our v0, is equal to v0. And this is, when I insert here 0 seconds, it would be 5 meters per square second times 0 seconds plus c. This term vanishes actually. So this is gone. And then at the end, what remains here is only our c1. So what it follows is that our c1 is equal to v0, and this is equal to our 3 meters per second. So now we can calculate our speed at a given time of 2 seconds. So this would be our 5 meters per square second times 2 seconds plus our v0, which would be 3 meters per second. And if I insert this at the end, we will get a value of 13 meters per second. And now we can do the same for the position of this car. So again, we can write here s of t, and we know already that this is the integral of vt dt. And we have seen that v of t is simply given as a times t plus c1. So when I integrate over at plus c1, this gives 1/2 at square plus c1t plus c2. And we have also seen already in it before that c1 is our v0. Now what we have to do, we have to determine our value c2. And again, we use our boundary conditions. So we know our initial position is at 0 seconds, which means this is S0, which leads to 1/2 times 5 meters per square second times 0 seconds squared plus our initial speed, 3 meter per second times 0 seconds plus c2. And again, we can see now that everything vanishes here except c2. So at the end, what remains is our s0 equal to c2. And this means c2 is equal to s0, and this is our 10 meter. And then we can easily calculate our position at a time of 2 seconds, as we want to do that. And this is 1/2 times 5 meter per square second times 2 seconds squared plus 3 meter per second times 2 seconds plus 10 meter. And if I sum up all these values, then at the end I get a value of 26 meter. So given these boundary conditions, S0, V0 and the acceleration, we calculate that our car has moved 26 meter. So we can sum up what we have learned before and then calculate a general equation for that. So as we said before, V is integral a dt, which is for constant acceleration at plus c1. And we have already seen that c1 is equal to our initial speed v0. So this is equal to at plus v0. Now we can calculate the speed of the object, and the same we will also do now for the position. So this would be s equal integral at plus c1, and of course the integral has to be over this whole term dt. And then we can calculate here, this gives 1/2 at square plus c1 t plus c2, and we know already that our c1 is again v0 and our c2 is already as given as s0. So now at the end, when we write this down, this is nothing else than 1/2 a t square plus v0 t plus s0. So these are actually also the two important equations that describe the motion of any object. So if a is constant, then v is equal to at plus v0, and s is equal to 1/2 at square plus v0 t plus s0. And again, this is very important, so I would like to highlight this in red. And this we will use in the next videos very often. We will use it to describe, for example, free falling objects or any kind of motion of objects within the gravitation field of the Earth. It will also come again, it will play an important role later in electrodynamics. So it's very, very important equations that we learned, and we should keep them in mind. So we can say that the position of any object is given by acceleration a, initial speed v0, and initial position s0. And of course, until now we only took a look at the one-dimensional case. So in general, we have of course vector form. So we can write in general, we replace s with the vector r, and then we can simply write 1/2 and then vector a t square plus v0 vector times t plus, and then not the initial position, but the initial vector for the position in three dimensions. So this would be our r0. And we can make another example for that. to again understand it and to learn it a little bit better. So let's suppose we have an acceleration which is constant, given in x direction with xy components as 0, and then we have an initial velocity given as 0, 10 meter per second and 0, and we have an initial position given as 0, 0, 2 meter in z direction. Then the position at any time, for example t equal to 5 seconds, would be given as r of t. First we have to calculate the integral. Yeah, so we can write here 1/2 times 5 meter per square second times t square, 0, 0, plus, and then we can write here 0, 10 meter per second t, 0, and then here we can write 0, 0, 2 meter. There is no change at all. So this at the end will lead to r of 5 seconds to 62.5 meter, and here we would get 50 meter, and here we would get 2 meter. Yeah. Okay, this is everything which I want to show today. Thank you very much for your attention, and hopefully see you soon for a new video. Thank you very much for watching this video. If you like the content and want to see more of it, any type of support is always appreciated.